the two theorems that we have to prove triangles are congruent are SSS and SAS, right? That's what we've been talking about. SSS is side, 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 right? And SAS is side, angle, side. Meaning you have to have the angle included between the two sides in SAS. Okay? Those are two we have. There are actually two more that you can use. Which is nice because then, depending on the proof, you can use either SSS, SAS. The third one is ASA, which obviously stands for angle, side angle. And the last one is AAS, which is angle, angle, side. Those are the last ones. So we now have 4 theorems that we can use to prove triangles congruent. These are used the exact same way as we did before, except we just have different pieces of information. This one, we would have to have 2 angles and the side that's sandwiched between them, right? The included side. This one, we would have 2 angles and then a third side. Doesn't have to be sandwiched between them. Okay. Now, I'm waiting for it. Nobody's asked, but is there such thing as an angle side side? Sorry, no, there isn't. You can't write that on your paper. If you didn't laugh, it might have went over your head. If you didn't laugh, it might have went over your head.
Okay. I wrote it down. I was like, no angle side.
These are the only 4: side, 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 angle, side, angle, side, angle, and angle, angle, side. Okay. So those are the 4 that you will use. Okay. They're used the same way, just different piece of information. So again, there is no such thing as angle, side, side. Okay. So let's walk through this proof together, and we're going to see which one we have to use here. This is just a general one that could show up somewhere maybe. In this figure, our goal is to prove triangle BCP. That triangle is congruent to RCP. That triangle. We want to prove those 2 triangles are the same. So to prove 2 triangles are congruent, you can use one of 4 things: side, 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 angle, side, side, angle, or angle, angle, side. You don't really know which one you're going to use until you start writing it out. Right? So based on what we're given, it says that CP, this segment, bisects, what does bisect mean? Cuts in half, angle BCR. It cuts that angle in half. So just from that little piece of my given, what am I going to know about these 2 angles? They're the same. So I'm going to go ahead and write that because I know that's probably going to come up. I know angle BCP is congruent to triangle RCP by definition of a bisector, segment bisector. Anytime it tells you something bisects, 99 to 100% of the time, probably 100% of the time, it's going to be, you're going to write what it bisects as congruent, right? Either a segment or an angle. The other piece of my given says it also bisects angle BPR, which is that angle. So what do I know about those 2 angles? They're also congruent by the same reason. Angle BPC is congruent to angle RPC. Again, the order doesn't matter as long as, in this case, P is the middle of both of them. So I'm going to go ahead and mark that. Then I know that angle is congruent to that one, and that angle is congruent to that one. So again, I have two angles of each of these triangles congruent, which means I probably don't have to use side, 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 because side, side, side doesn't use any angles. I probably am not going to use SAS, because that only uses one angle. I'm probably going to use either angle, side, angle, or angle, angle, side. The difference between them being which side you have. One of them you have the side between the two congruent angles, and one of them you have a side outside the two congruent angles. So that's all I'm given, and if I look at this triangle here again, I have two angles are congruent. And this triangle here, I have two angles congruent. Do they have a side? Do these two triangles have a side that's congruent? Yeah, true. Yeah, CP is congruent to CP, right? The side is congruent to itself. That's the side they share. CP is congruent to itself by the reflexive property. So that side's congruent to itself by the reflexive property. So now looking at these two triangles, again that one and this one, I have three pieces of information. Of this top triangle, I have two of the angles congruent and a side. Do I have the included side or do I have a side outside the two angles? Meaning, do I have the side that's sandwiched between the two congruent angles? Yeah, I do, right? That's the side between the two congruent angles. In this triangle, do I have the side sandwiched between the two angles? I do, right. So is this going to be AAS or ASA? Angle, side, angle. Those two triangles are congruent because I have an angle, a side, and an angle. And here I have the same angle, side, and angle. So that's a proof using angle, side, angle as an example. I'm proving two triangles are congruent. I used angle, side, angle. Any questions with that one? All right, I want to look at one more here. All right, so here, my ultimate goal here now is not necessarily to end with two triangles that are congruent. I want to end with AE, this piece, congruent to BE, which is that piece. Okay. I want to show those two pieces are the same somehow. Whenever you need to show two pieces of a triangle are the same, if you can prove that those two triangles themselves are congruent, you could say by CP, CTC, those pieces are the same. Right? See what I'm saying? So if I can, in some way, show that this triangle is congruent to this triangle, I could match up their sides, right? This side would match up with this side of the green one, okay? And AE would match up with BE of that one, right? If these two triangles were the same, if the green triangle was the same as the yellow one, these two sides would match up, right? So let's try and prove that triangle ADE is congruent to triangle BCE. Because if we could prove those two triangles were the same, again, that's that triangle and that triangle, then I know the sides that would match up would be BE and AE, right? Which is what I'm trying to prove. Okay. So let's look at how we can prove these two triangles are the same. First of all, if they ever share a side, we can always say that side's the same by the reflexive property. Okay. Do these two triangles share any side? Do these two triangles share a side? They don't share an entire side, right? Yeah, they do share a piece of a side, right? So the other piece of my given, let's make sure I have my given marked. EAD, that angle, which I have marked, is congruent to EBC, that angle, which I have marked. And AD, that piece, is congruent to, AD is that entire piece. So I should mark that. AD, that entire piece, is congruent to BC, that entire piece. Right? So of those two triangles, I have a side that matches up of each, this green side, and I have an angle that matches up of each. I only have pieces of a third side that I can do. So let's go back and look at these triangles again. Do they have any angles that they share that are the exact same? Do they have an angle that they share? Yeah, good. Yeah, they share DEC, this angle right here, right? So just like sides, you can say angle E is congruent to itself by the reflexive property. Again, I just used one variable. It's probably better to use three if you can, but I only used one just because there's only one angle that could be, right? For example, I wouldn't want to say angle C because I don't know if it's that angle or that angle. But angle E, it's just that one. Okay. So now let's look at these triangles. I'm looking here, and I'm looking here. I only have one of their sides are the same, right? And that's this green side I marked here. That side's the same as that side. But I have two of their angles are the same. Is that the included side? Like, for example, is this ASA? I would say it's not because there's my two angles. That means the included side of the yellow triangle would have to be BE, right? But I have the side that's outside that. I have two angles and the side that's outside those two angles that's not included.
Well, isn't it in between them?
Right? If I'm looking, let me back this up. Let's just look at the yellow one here. I have two angles and then this green side, right? So in order for it to be the included side, it would have to be this one, right? Because then it would be angle, side, angle.
And you can't cut the one going in between because it's not on that triangle.
Right. Here I have this angle, and then the side on the outside. Of the other triangle, I have an angle, and the side on the outside. But luckily we have a theorem that lets us use that called angle, angle, side. If you have two angles and the side that's not sandwiched between them, that's still enough to prove triangles are congruent. So I can say these two triangles are congruent by ASA, which means that triangle matches up with this one. Therefore, AE and BE match up because of CPCTC. So it's kind of in reverse there. Instead of giving you a congruent triangle, you had to prove a triangle is congruent and then tell me which pieces match up. So that's kind of a difficult one. Okay, but that would be an example of AAS. Yes?